Hi, I'm Samir Ajmani. I work here in New York. I'm joined by my colleague Alan Donovan, who is writing the aforementioned book. I'm a tech lead manager for about a third of the Go team. The third I manage works on two major things. First of all are the Go libraries that we use internally to Google for accessing Google infrastructure. And second are all the libraries and framework support for running Go on mobile applications, which you can think of as Go's client-side story, getting Go code to run on iOS and Android devices. I'm going to talk to you today about Go in general, and I've done my best to customize the material for Java programmers. And I'm going to spend a little time talking about what's similar and what's different between the languages and why. But the bulk of the talk will be working through some extended examples, including quite a bit about concurrency. General outline, what is Go and who uses it, comparing the languages, the examples I mentioned, and a brief discussion of some of the tools that are available. So the tagline from Golang.org, which is the homepage for the language, is that Go is an open source programming language that makes it easy to build simple, reliable, and efficient software. The real key phrases here to understand and remember is, first of all, it's open source. It's been in open source development since 2009. The compiler, the runtime, the standard libraries, a whole variety of additional repositories are all available free and online, and we get a lot of great contributions from the open source community as well. The other is simple, and this is a debatable term. Everyone wants to believe that what they've got is simple, but I really think that Go is pushed for simplicity in the language and in tooling in a way that I personally found quite refreshing, having come from a background doing C++ and longer ago Java as well. And I hope to get that across to you in this talk. Go began back in 2007, and as legend tells it, Robert Breesemer, Rob Pike, and Ken Thompson were waiting for a large C++ program to compile, and then started talking about everything that's wrong with the world. But what you need to remember about 2007 is that at Google, things were getting big. The company was growing, the products were growing, the software was growing, the number of queries per second, the amount of data we had to move around, everything was getting big. We were building larger and larger data centers, the machines were becoming massively multi-core, and things were starting to show the strain. Build time was just one piece of evidence here. So they started thinking about ground up, what can we do about these problems? And I'll get more to that in a minute. They were joined pretty soon thereafter by Ian Taylor and Russ Cox, and this team, they built the compiler, the runtime, the libraries, and were open source the language in 2009, as I said, a very active community. And as of 2012, the language is stable, which means that since then, programming writing Go will continue to compile, but standard libraries are also guaranteed to be backwards compatible going forward. That's the Go 1 guarantee. And that is part of what's allowed us to really grow the language and have it be more and more widely adopted. So why Go? Go is an answer to the problems of scale at Google. Here's a picture of one of Google's data centers. We've got a lot of these. They each have a lot of machines. And the way we build software in Google involves writing jobs that span a massive number of machines. And what that means is that we had a new design point, which is we needed to embrace the notion that we may have software that's running on millions of machines. It's routine and every day now to run jobs that are on thousands of machines. In a given job, we have a set of replicas all the same program. Of course, you've got structure with them all communicating. And then, of course, between jobs, there's a massive amount of communication, typically using RPC, but there's other protocols as well. There's a lot of concurrent interaction between elements of these systems, in these distributed systems. You're all familiar with these sort of layered systems as well. There's a lot going on at once, and they can be very tough for developers to grasp and understand. It's tough to keep things straight. And what we're looking for is a way to help developers organize their model of what they want to be going on in their programs. And so we need a language with great support for concurrency. This little diagram comes from a great talk by Rob Pike called Go Concurrency Patterns. It's worth reading. Now, actually, one of the examples that I'm going to be using comes from that talk as well. But yes, so Go first. also demoed here, are the Go mascot, and these are also going to be distributed at some point tonight. The second problem, of course, is engineering scale. It's that Google is massively growing. These are intentionally stale numbers. So back in 2011, we had over 5,000 developers in 40 offices. Rapid rate of change to the code base, a lot of turnover in the code base. Testing that, so we had a single code tree where then we were testing all the changes every day, as changes went in. And so we needed a language and a development system that allowed us to keep growing along in this way. That builds had to be fast, tests had to be fast. Changes, it needed to be also obvious to reuse the work that had been done before. And then when developers are reasoning about the code base, you need to be able to do that in a reasonably modular way, where you didn't have to go grubbing through a huge amount of code you'd never seen before to understand what was going on. All right, so let's talk about who's actually using Go today. At Google, we've got lots of projects using Go, thousands of Go programmers, millions of lines of Go code. Go is using Go in a big way. Google is using Go in a big way. A few I can talk about publicly. One is a data compression proxy that your mobile phone would use. If you're using Chrome on a mobile device and you're accessing an unencrypted site, it'll go through that proxy and you'll download less data to the same website. Another two, the download server, the one that you download Chrome from, or Chrome OS, or Android SDK, or Earth, that's front end is written in Go. So that's a case where we're delivering large data objects from Go front ends. And then the YouTube MySQL load balancer called Vitess, that's open source. It was one of the earliest adopters of Go in a production environment. Massive number of queries per second. Every YouTube database hit is going through a Go program. And this is providing them things like connection coalescing and caching. So the target from early on was network servers, but the surprise has been that Go's worked out really well as a general purpose language. One of the groups that really has been adopting Go in a big way are people coming from dynamic languages like Python and Ruby, who find that they can be just as effective with Go, if not more so, because it's building really fast. They're not losing a lot of time switching to a compiled language, but they're getting a lot of the additional guarantees and performance from what Go can provide. So who uses Go besides Google? There's a wiki page. This is a fraction of that list. It's a long list. Thousands of companies, or sorry, hundreds of companies at least, and thousands of open source projects are using Go. Some names I'll call out from here: DropBox, Facebook, New York Times. A lot of these are writing, servers in Go, but there's also a lot of infrastructure and tool companies in here. Docker and Kubernetes, I'll call those out. Go seems to be pretty popular with startups. I think startups, you have the opportunity where you don't have a big legacy code base, and so you have a chance to try something new. And it seems to be sticking. At GopherCon last year, yes, there's a GopherCon, there's another one this year. CoreOS had a bus with the Gopher on it. It was a great surprise, it was hilarious. All right, so let's talk about Go and Java. So Go and Java have a lot in common. The thing to remember about Go is it's written with hindsight, so we get to look at what's come before, that includes C++, that includes Java, and see what are the parts that say, yes, those are working out well, we definitely want those in a new language. We also get to say no. So what we said yes to, that you'll recognize, we're in the same family, it's imperative code, sort of curly brace complete. It's statically typed, it's garbage collected, it's memory safe, we call them null, nil, but it's nil references and runtime bound checks. Memory is always initialized, so things have the obvious zero value, whether it's zero or nil or false or the empty string. Types can have methods. Methods can satisfy interfaces. Given an interface value, you can use a type assertion to figure out what the concrete type is or see if it implements other interfaces. And there's a support for reflection as well. So that all should be very familiar. Some interesting differences. Programs compiled to machine code. There is no VM. Go is designed to go from the metal up. Again, getting to system software, we want to develop high performance software here, so we need to be able to, that's the model. Produces statically linked binaries. Deployment is very easy. You just copy it where you want it and run it. Go also has good cross-compilation support, so you can build for Windows, build for Mac, build for Linux, whatever you need to do. One important difference is that Go gives you a lot of control over your memory layout. I said we have types, and types can be you can have deeply nested structures that are entirely flat in memory. Think back to C, okay? Having a reference to another structured type doesn't mean adding an indirection. And so this means you can control the amount of allocation you actually have to do in the program. This gets important when you're trying to optimize for the amount of garbage you're creating in your program, as it is a garbage collected language. So this gives you a way to trade off against that. Functions are first-class values in Go. You can pass them around, you can return them. And furthermore, we have lexical closures. It's a little bit like lambdas, but a little more powerful because you don't have to just close over final values. And we'll see that a lot in the talk. Go has several built-in types. It has built-in strings. Go source code is Unicode encoded in UTF-8. Strings are as well. It has built-in generic maps and arrays. Mostly you don't see arrays in Go. You see slices, which are views on arrays. You'll see those quite a bit in the talk. And of course, built-in concurrency, and there's certain data types associated with that, namely channels. Finally, Go intentionally leaves out many features. This is a short list of things you're not going to see in Go coming from Java. There are no classes. There are types, and they can be structured. They can have methods, but there are no classes. There are no constructors. You have functions. Functions can return values, right? So what you would think of as, I guess, a static factory or a factory function in Java is how you would create a new instance of a type that needs to satisfy some invariants. But there are other things you do, and again, I could get these in examples that often obviate the need for them altogether. There's no inheritance. Use composition and delegation. The language does give you some support for sort of canonical forms of delegation. There's no final. There are no exceptions. Go has error handling. It's very, but we treat error handling as not exceptional. It's routine. It's something you do in system software. You just deal with errors. Errors are regular values. We'll see that again in the examples. There are no annotations. And finally, there are no user-defined generics. This tends to be a sticking point for people like, how can you have a modern language that doesn't have generics? Part of it is that we have those built-in generic maps and slices and concurrency stuff. And part of it is you have interfaces, you have function values. And it turns out that once you have that as a foundation, user-defined generics, on balance, aren't nearly as compelling as they seem to be. Now that's a tough argument to make. I'm happy to sort of hash that out over beer. But for now, I'm going to focus on the examples and hopefully get across that the code actually works really well, even so. All right, so why does Go leave out these features? The answer is clarity is critical, and this gets back to engineering skill. We want it to be the case that when you're reading code, it's clear what the program's going to do. This means keeping the language small. This means making sure there aren't too many different ways to do stuff. There are a lot of idioms and conventions in Go so that the code looks very natural and very familiar regardless of where you go, and there's a lot of effort we go to make that happen. When writing code, it should be clear to how to make the program do what you want. Again, it gets back to those idioms and convention, and that the language is small and gives you have fantastic libraries, but the core components, the amount you actually have to keep in your head is fairly modest. Sometimes this means you write out a loop instead of invoking an obscure helper function. We think that's the right trade-off to make. 3 little lines that are very obvious is better than a function that you have no idea what it does. Little tagline here, don't dry out. You hear don't repeat yourself all the time? It can be overdone. So we'll see that. For more background on design, Rob Pike has 2 great talks back in 2012. One's called Less is Exponentially More, and the other one's Language Design with Services Software Engineering. Look them up. All right, let's get to the code. So Go looks familiar to Java programs. Here's Helloworld in Java, at least as far as I remember it seems to run. And in Go, your program starts in func main and package main. And here I'm importing a package called funct. Funct has a function called printline, and I'm saying, print hello world. And if I click this little run button over here, now it's going to compile and run my program. So there, hello world. Program exited. Here I'm showing off the Unicode strings just a little. So let's make it internet enabled. So here's hello as a web server. My main function is going to register a handler for the hello endpoint, and that handler is going to dispatch the function handle hello, which is defined below. Can you even see my cursor up there? Yes, you can. Great. It's going to print a string saying serving on this host and port, and then it's going to invoke HTTP listen and serve, which is going to block and serve on that host and port. And if that ever returns, so it can't find the port, it's going to fatal out with a log message. The handler, in turn, it's going to take 2 parameters. It's going to take the HTTP request and a response writer, which can allow it to write back to the client. It's going to print the URL it's serving. It's going to print hello world. So let's run that, and then I'll get more into exactly what's going on. So I have that. There we go. Oh, fantastic. And here you see the log message from when it served that endpoint. Okay, so a few things to note here. HTTP, this token refers to this imported package, not HTTP. This is again provided by the Ghost Channel Library. It provides an HTTP server and an HTTP client. And when I said handle func, this is registering a handler in the package level registry. You can define separate muxes for your HTTP stuff, but it has convenience functions in a global registry as well. And that's what I'm using here for the example, but obviously you can have more elaborate dispatching if you need it. Down here in the handler, I'm using that func package again, someone I used in Helloworld, but here I'm writing to a response writer. What's going on here is that we're using an interface called IO Writer. IO Writer, I'm going to show it to you a little bit later, but the func package knows how to write to IO Writer. It's analogous to, you think, maybe Java's output stream, and HTTP Response Writer implements that interface, and that's what's allowing this all to glue together. A bit about syntax. Types follow the names and declarations. I know it looks backwards to you, but there are reasons why. So response write is a type of the W parameter here. HTTP request is a type of the request parameter here. The little star here is a pointer. Some of you might remember this from C. So HTTP request is struct type. This tells you got a pointer to that. That gives you a way to mutate the value. It's a reference, right? A bit about capitalization. So actually similar to Dart, there's only two sorts of visibility. There's package visible, package private, and there's public. We call that exported and unexported. So exported names are capitalized. So response writer is an exported name from the HTTP package. Unexported names like handle hello start with a lowercase letter. And that's it. That's the visibility rule. It turns out to work really well, actually. So for a more extended example, before we get to the concurrency part, I'm going to present you a little Google search front end. Here's a screenshot, since I wasn't sure if the network was going to work, but it does. We're going to be able to issue a Google search query to the search endpoint, just using a little query string. And this is going to fetch that using a Google API call and render the results as an ordered list and tell us how many results it got and how long it took. The main function looks just like we saw before, except for now I've got a search endpoint and it's going to dispatch the handle search function. And handle search here has the same signature as handle hello did before. Here you see sort of a typical Go dot comment. Handle search handles URLs like yada yada by running a Google search and writing the results as HTML. So if I pull that up, oh, we're in Java. Let's search for Java. All right. Oh, my network. The network is down. Okay. So, all right, the network's down. Sorry. So maybe if I can get the network back up, this will actually connect. But what that's telling me is that I wasn't actually able to connect to Google. Sorry.
Maybe Google's done.
That would be, that's fine, everything else is working. Now we can get but again, the screenshot shows you what you would actually have seen anyway, except for Java and not Go. All right, so let's walk through this code. This is going to be several slides long, but it'll introduce various features of the language as we go. Here's the beginning of the handle search function. The first thing we're going to do is validate the query. When we have this HTTP request, we print that request URL, and then we extract the form value Q, right, whatever the Q parameter was in the URL, and store it in this variable called query. Now, there's a lot going on in this line. First of all, rect.form value, this is a method call, familiar syntax. If we look down at the HTTP package, what you see is there's a type like declaration for request. It's a struct type. Struct just means it's a record type with multiple fields. The method declaration looks like this. Form value is over here. What you see before the name of the method is the receiver, right? And this is what associates this method with this data type. And in Go, receiver is really just another parameter to your function. It's just special in that it gives you, in the way it associates with it, but you're naming it the parameter R, and that's what you're going to use in the body of the method. You're going to call the receiver R. The parameter it only takes one parameter, which is key. It's a type string, and it returns a string. So return values over here on the right. Don't get hung up on the reversed syntax. It takes an hour of getting used to it, and then you're done. It's fine. What's more interesting here is this colon equals syntax. This is a short variable declaration. Actually, we saw something again similar to like this in Dart. I could in fact have typed var query, and again, it's declaring query and say initializing it to have the type of whatever's on the right-hand side. In this case, a string. I could say that query is a string, and then obviously if I said query is an int, the compiler will fail. Right? But this pattern is so common that Go supports it as colon equals, right? So now that we have our query, we can fetch our search results. And for this, we're going to call a helper function, also defined in the same file called search. I'll show you that a little later. We're going to time how long the search took to run. So we're going to grab the current time. It is using a function in the time package, time.now. It returns a value called time. That's going to be in start. And then after the search runs, we'll calculate the time elapsed since it ran. And that's what gives us that 37 milliseconds we saw earlier. Elapsed has a data type time.duration. That is the duration type from the time package. It has a string method that prints out that 37 milliseconds for you. One thing that's interesting here is that we've got two values on the left-hand side of this assignment, results and error. Go functions and methods can return multiple values, and in particular, they can return a value of type error. Error is a built-in type. It is an interface type and an interface type is just something that just defines a set of methods. The error interface only has one method defined on it, which is also called error, and returns a human-readable error message. But of course, errors can contain structured information. You can introspect them with type assertions. But this is sort of one of the fundamental differences between how you program in Go and how you program in languages that use exceptions. You get an error, you check the error. If the error is not nil, if it's there, then the rest of the results in the function are, you expect not to use them. They're invalid. In this case, we handle the error directly by sending the user a status page with the error code, server internal status error. And we're going to include the string in the message and generate that right into the response writer, and bam. Here's the signature of that search function. It takes a query. It's returning a slice of results. Again, that's a view on an array, a hidden array of results, and the error. And we'll get to the body of that in a minute. So if the search succeeded, now we can go ahead and render the results. Here we're using a data-driven template. The data we're going to use for the template are the results and that elapsed time. I'm going to define a local data type here called template data. It's a struct with these two fields. This is local inside my handle search function. So being able to define these little structs in line and these types in line can be very handy for doing things like this. This here is a struct literal. It is a way of creating an instance of this value, and I'm specifying that the results field of this struct comes from my search, and the elapsed duration comes from that measurement when I did time.since_start, right? And I'm going to execute the template with that data. It's going to write out to that IR writer, to that HTML response writer, and then if there's an error, I'm going to log an error in return. So results template.execute. Again, this is using an IR writer interface. Here's the interface. It has a single method. This is one that's sort of analogous to output stream. Write takes a slice of bytes and it tells you how many bytes it successfully wrote and possibly an error if it failed. And so response writer implements that IR writer interface. So the template is going to operate on, again, a slice of results. It's going to operate on that template data, which has the results as well as the elapsed time. It's specified here in a raw string. Here, it's the HTML head and body and whatnot. Here's the order list, and here's the syntax that users reflect over the data we've provided it. It's going to range over the list of results, and for each one, generate a list item with the title, the URL as a URL as a link, and then after the list, give you the number of results in the elapsed time. And so the result type, each one in our list is just a struct with both the title and the URL string. And so to remind you what that looked like, we'll go back to that screenshot. You just get, this is the rendered HTML from that template. All right, moving on now. The search function, this is one that's going to make a call to that search backend. First thing to do is prepare the URL. This is going to use the standard library's URL package, parse the URL, check for errors, and set the query, encode it. And now we're going to use the HTTP package get function. It's going to block, it's going to fetch the URL, return the response. One thing to note here is we're just calling blocking functions. And, as mentioned earlier, this can take a while, right? And the key thing is that this is Go style. If you write straight line code, you block when you have to, and concurrency is something you're going to add on top, and we'll get to that in detail in a few minutes. But it's important to note that writing straight line code without doing a lot of inversions through callbacks or even futures makes it much easier to understand. We get this response. If it's all right, now we can consume the body. An HTTP response, the body is potentially a stream, right? It actually implements IO reader. This is the complement to IO writer, like an input stream. And part of the contract is we need to close it when we're done, because that allows the HTTP package to then clean up the connection, release any resources associated with the stream. The way we're going to arrange to do this is with a defer statement. Defer arranges for a function to be called when the calling function returns. It's a little bit like a finally block in Java, except for you don't have to create a whole new scope around it to arrange it at the end. You just say defer, and that puts it on a stack. And then whenever the function returns, it's going to run the deferred functions in last and first order, out of order. That order is very handy for doing things like unlocking locks you've acquired and other things that are sensitive to that sort of order. What we got from the Google API request is a JSON type, which I could show you if the network is working. Sadly, it's not. What the JSON response contains is a big field called response data, and then a list of results, which have fields called title, no formatting, and URL. What I've defined here is a Go data type that mirrors the JSON, right? It has fields that have the same names as what's in the JSON. And furthermore, you'll notice there's no type keyword here. I've just defined this as an anonymous type just for this variable JSON response, because I'm only going to use it the once. So I don't even have to declare it as a named type. Oh, that's interesting. Ha! I guess so. Now it's trying to be helpful and get me to log in.
Slow down.
That's all right. I'm not going to bother. It's fine. Huh?
You might get your network back as a demo.
I suppose. All right, let's see if my... Yeah, but I need to go look up the passwords. Oh, you think it's all saved? Nope. Oh. Oh well. That's all right. We'll soldier on. So the important thing to note here, though, is so I've just defined a Go struct that mirrors what I'm getting from JSON, and I'm going to hand a JSON decoder the response body and tell it to decode in this Go value. It's going to use a reflection to then map the corresponding JSON field over my Go value. And on success, now I have a Go data type that has exactly the data I wanted from that JSON. And of course, there's a JSON encoder that does the opposite. I can create a Go data type and then encode it, and it'll create a JSON that mirrors it. And we have the same thing for XML. We have the same thing for a variety of other encodings, where you can get this very clean mapping between your statically typed Go program and these various serialization forms. Finally, to wrap this example up, we're going to iterate over the JSON response and append our results to our return value and return it. And we're returning nil here for the error because we succeeded. That's it for the front end. Okay, that wasn't very short, but that's a complete example, and it used all the packages it used from the standard library. So you saw JSON encoding and decoding, you saw HTML templates, you saw HTTP and URL parsing, as well as other basic stuff. The other good news is that server's going to scale pretty well. You can throw thousands of requests per second at it, and each request is going to run in its own lightweight thread called a Go routine. And even though I was making those blocking calls at the back end using HTTP GET, the system, the runtime, is going to handle multiplexing that and making sure that it consumes only a very modest number of operating system threads. So let's talk about concurrency, because that's really where Go shines. Go's concurrency model is based on CSP. Communicating sequential processes were introduced by Tony Hoare back in 1978. The basic idea is that concurrent programs are structured as independent processes. And here I mean logical processes, activities, not OS processes. Independent activities or processes that each execute sequentially and communicate by passing messages. Not unlike the isolates you saw in Dart. And the motivation here is sequential execution is really easy to understand. You know, all that code I showed you read top to bottom. You could go line by line, see what's happening. The error handling was all top to bottom and sequential. If it needed to block, it just blocked. Sequential execution is really it's easy to understand. Async callbacks, not so much. I don't know if you guys are familiar with callback spaghetti, dealing it from JavaScript in particular. I dealt with it in C++. It's not pleasant. But straight line code is an important part of comprehensibility, and so we want to have our cake and eat it too. We want highly scalable programs that are easy to understand. On the topic of sharing memory, now Go is a shared memory model. You can have multiple Go routines using the same memory. It is possible to create data races. However, by using communication, you avoid most of them. Right? You can safely pass data back values between these lightweight threads and avoid the data races entirely. So the tagline here is, don't communicate by sharing memory, share memory by communicating. The primitives in Go routines, channels, and the select statement. Let's go over those and then we'll get into the example. Go routines are like lightweight threads, but they're managed by the Go runtime. They start with tiny stacks. The current implementation is a 4K stack, and they resize as needed. So if your Go routine executes a deeply recursive function, that stack will grow dynamically. It will also shrink as needed. What this means is Go programs get hundreds of thousands of these things. You just use them freely. It fundamentally changes how you structure your program when you don't worry about the overhead of starting these things. The syntax is also quite simple. Instead of invoking a function, you say go in that function, right? This looks a bit familiar, perhaps, if you remember the defer statement. That was defer in a function net, arrange for a function to run at, on return. Go in a function, arrange for a function to start executing a new Go routine. The Go runtime schedules Go routines onto OS threads, so you can have hundreds of thousands of Go routines, where the number of threads that just set to be, say, the number of CPUs or some small multiple thereof. Blocked Go routines don't use a thread, so when you're blocked on I/O, you get tossed into an epoll. Even then, this is one part of it allows Go to scale really, really well. Channels provide communication between Go routines. You can think of it as type synchronized queues. Here I'm making a channel whose value data type is string, and I'm putting in the variable C. In one Go routine, I can send a string like hello on the channel, and in another Go routine, I can receive from that channel and store it into a new value, say S, and then print that out. I'm using this little arrow syntax for both send and receive. Send is a statement, and receive here is an expression. It can be used wherever an expression is. The important thing to note here is that it's blocking communication. So this send statement is going to block until some Go routine is ready to receive from that channel. So it also serves as a synchronization point. You're going to use this when you create concurrent programs, because once you know you handed off a value, then you've just essentially transferred ownership to that other program, to that other Go routine. You're not going to use it. The receiver now has an opportunity to use that value. Obviously, values like immutable strings are safe to be shared across Go routines, but if you're transferring a pointer, you've handed it off. The select statement allows Go routines to multiplex their communication. It looks like a switch. Go does have switch, but select is specifically for dealing with channels. Each case in the select is a communication, either a send or a receive. In this case, the first case is a receive, and the second one is a send. The first case, I'm receiving from a channel called in, and if this communication runs, if this is the one that's selected, then the receive will happen, the value will be stored in the variable n that I've initialized here, and it'll print the value I received. If instead the send happens, then I'll print that I sent that value. And only the selected case runs, right? If one happens, the other one doesn't, so that value isn't consumed. So let's see how all that fits together in a reasonably real application. We saw the Google search front end before that made the API call. Let's talk a bit about what it looks like in the back end. So what does Google search really do? Well, given a query, you get a page of search results and probably some ads. How do we actually get those search results? Well, what we're going to do is send that query to several backends. Web search, image search, YouTube, maps, news, the ad server. Excuse me. And then we're going to mix the results and try and provide you the best web page we can that we think satisfies your query. So how do we actually implement this? Now, we're not going to do all of Google here, so we're going to fake it out a bit. we're going to simulate the web image and video searches with a little fake search. And what a fake search is going to do is it's going to sleep for some random amount of time from 0 to 100 milliseconds, and then it's going to print how's a web search result for whatever query you gave me. Search here, we've defined it to be a function that takes a query and returns a result. A result is also a string. And fake search is going to, here we're using Go's lexical closures. It's going to return a search, it's going to return a function that's now closed over kind. You can hand it any query. So how does that actually look like in practice? Our main function, we're going to call a function called Google. We're going to hand it the query golang, we're going to get the results. We're going to measure how long it took to run. We're going to print the results in elapsed time. So here we got a web search, an image search result, and a video search result, each for that query, and it ran in about 150 milliseconds. If I hit this a few more times, you'll see it's sticking pretty close to 150 milliseconds. Here's one that was a little longer, over 200. Here's one that's under 100 milliseconds. And the reason that time is in that range is because we're making these calls serially. So we're making the web search, the web query, we're appending its result to our slice of results. We do the same for image, do the same for video. Each one is a random sample between 0 and 100 milliseconds. That's why we're converging on that 150 millisecond average. Now, web, image, and video are all independent. There's no reason to wait for web to complete before issuing image. So we want to run them in parallel. This is the same code, the same Google function now with running those three in parallel. We're going to start a Go routine for each backend. We're going to collect the results on a channel, and then we're going to append those to our result. So what I've done here, we're going to flip back and forth for a second. Here we just had web, and we're appending it directly. Instead, I'm going to run web in a new Go routine. Now, when I showed it to you earlier, I said Go f of r's. The same thing is happening here, except for my function is being defined in line. This is just a little closure. It's an anonymous function, and all the function we do is invoke web and send us results on the channel. I do the same for image, I do the same for video. This channel is a channel of results. I know I'm going to get three things back, so I iterate 3 times. I receive from the channel and I append it to my results. So now when I run it, I get web, image, video, and image in 77 milliseconds. Again, 86 milliseconds. Again, 68 milliseconds. Oh, but now video came first. Well, what's happened here is that video was the fastest. So it got received first. So the order is now non-deterministic. But the runtime is the runtime of the one that took the longest. So it's going to skew high, right? You're going to see mostly 70 and 90 milliseconds, or 50 if you want. Great, so now we parallelized our backends. Wonderful. But of course at Google everything's about speed, speed, speed. 90 milliseconds is just way too slow. So let's set a timeout. Let's say that we are not willing to wait any more than 80 milliseconds for any of these backends to return. How are we going to do that? Here's where that select statement is going to come in. We're going to start a timer, and we're going to use this special function, this function in the time package called time.after, which is going to return to us a channel. And we're going to call it channel timeout. And that channel has the property that we can block and receive from it, and it will receive a value from the time package after that amount of time has elapsed. So after 80 milliseconds, a value will arrive. Got it? So now, inside our loop, we're going to select, and either we get a result from one of the backends, in which case we just append it, or we get the timeout, which means our 80 milliseconds have run out, we're going to print timeout, and we're going to bail. So we made it, this time we made it in time. We made it in 71 milliseconds, so we got all the results. 72, 61, oh, come on. Oh, there was a timeout, it went too fast. Okay, here, 80 milliseconds, you can see timed out, video was too slow. So video was somewhere between 80 and 100 milliseconds there. Now, take a minute and think what this would have taken in your favorite language, whichever it may be. No locks, no condition variables, no callbacks, no futures, no actors. One of the key things about Go's concurrency design is that it fits well with imperative programming. It fits well with the programs you're used to writing already. And this is one of the things that we believe makes it something that people want to adopt, that people want to use, because this code, while there are some new things to learn, we believe is fairly straightforward. We believe you can read this top to bottom and understand what's going on. And I'll put all these slides online, by the way. So how do we avoid timeout, right? timing out sucks. We don't want to lose search results. So we're going to throw money at the problem. We're going to replicate our servers. Instead of having just one web server, we're going to have 10, or in our case, 2 of them. And we're going to send our query to all the replicas. We're going to take whichever one comes back fastest. These are also known as hedged requests. If you've seen Jeff Dean and Luis Barroso's tail latency talk, he gets into these sort of techniques. So we're going to create this little helper function called first. First is going to take a query and a list of replicas and return a result. This ... syntax means a variadic function, right? So you can just comma add additional replicas on the end, and what the data type you get inside the function is just a slice. So we're going to create a channel of results inside this first function. We're going to create a little closure that's going to search the ith replica. And then for each of the replicas, we're going to start a go routine to search that replica. And then we're going to return whatever comes back first on that channel. Now, when we return, those other go routines continue running. And they are still going to sit there and block sending on this channel. And they will hang out there and block till kingdom come. Go routines aren't garbage collected. They need to return if you want them to go away. The way we handle this here is with this additional parameter to this channel, what allocates a buffer. So I said, when you just make a channel of send blocks until there's a corresponding receive, a buffer gives you some looseness, right? It allows the channel you to send up to some fixed number onto the channel without blocking, and then receives will receive it, just like a FIFO queue. So since we know that we'll have at most len replicas, or really len replicas minus 1 elements in this channel, we just allocate a buffer here, and now we know all those go routines are going to send on the channel, they'll return, the channel will have no remaining reference, it'll be garbage collected as usual. Okay. So let's see how that first function works. Here's just a little demo program where we send golang to replica 1 and replica 2. And so we're going to see replica 2 returned in 25 milliseconds, replica 1 took longer, right, and we don't see it here. So replica 2 seems to be winning. Here's replica 1 at 8 milliseconds. And what we expect to see is this should skew short, right? We should see more single millisecond, low millisecond times because this is smaller of 2 random samples between 0 and 100 milliseconds. So let's put it all together. We've only changed these 3 lines now. In each go routine, we're going to call first with our query. We're going to hand it a couple of replicas. We can add more replicas if we want. So I have 2 for web, 2 for image, 2 for video. And now when I run, so I got a web result from replica 2, an image result from replica 1, a video result from replica 1, and I ran at 69 milliseconds. So let's run this a few more times. Timed out. What happened here? Well, we had 2 image replicas. But if they're both slower than 80 milliseconds, we still time out. So fast by default, and sorry image, you were too slow. But for the most part, we should do better. We've brought our tail latency in because we're using these hedged requests now. We should see our latency skew down. And still no locks, no condition variables, no callbacks, no mess. In a few simple transformations, we've taken a slow, sequential, failure-sensitive program, timeout-sensitive program, and converted it to one that's fast and concurrent. It's replicated. It takes advantage of replication. It's robust. This is the critical thing we need to work at scale. This is the critical thing we need to tolerate failures and make stuff that's responsive to users. Let's talk a bit about tools. So Go has great tools, and this is by design. The language was built for tooling, and this gets back to that engineering skill point. It's not enough to make a language attractive to the programmer and fun to use, although Go is all those things. It has to also be something that allows a programmer to leverage the computer to become more productive. That means code comprehension. That means refactoring, but it also means simple things like formatting and inserting imports and building and things like that. So I'm going to go over some of the basic tools we've got. And the language is designed for machine transformation and maintenance, and we do a lot of that inside of Google. We have the access to the entire source tree, and we do global transformations on those millions of lines of Go code all the time. So Go Funct and Go Imports are 2 of our tools. Go Funct formats Go code automatically. There are no options. There is one standard Go format, and everyone uses it. And it's fantastic. Go Imports is just like Go Funct, but it has the additional property that will update your import statements based on your workspace. So you just write your code, and then usually as a save hook, your imports get updated. And I would show you a demo if I had a network. But just trust me, it's kind of magical, actually, because I've you just don't think about it anymore. Go imports is allowed to be wrong. You know, if I say JSON whatever, and it imports one JSON package, if I wanted a different JSON package, I just correct the import, and Go imports will preserve my correction. It's not going to, you know, it trusts the user. But Go font is really the thing that's just, you know, we enforce it as a pre-submit in Google. You cannot submit code that's not formatted properly. It's not allowed. It's great. The Go tool is how you build Go programs, and it allows you to do a variety of other things as well. It builds Go programs from source in a conventional directory layout. You don't need any makefiles or configs, YAML, or otherwise, because each source file says what all of its dependencies are. The dependencies are strict, and they are ordered. You can't have cyclic package dependencies in Go. So the program I'm using right here to present this talk and to run those demos is called Present, and it comes from the Golang tools repository. And you know, it's under the directory command called present. And so I ran go get in that path, and it fetched present. You realize that present needed the WebSocket library from the net package. It fetched WebSocket, it built everything, and it installed it on my path, and then I ran present. And that's it. Even better. So GoDoc is a lot like JavaDoc. You can run it from command line. But what's cool is that there's godoc.org. And it is a generated documentation for the world's open source Go code. You go there, you search for what you need, you find usually a dozen or more packages sorted by how much they're used, and you say go get, and you move on with your life. It's a very vibrant, active community, lots of open source Go code. You saw all the companies that are using it. They all love to share. IDE and editor support. If you search Google for Golang IDEs, you want to use the keyword Golang, searching for Go, just Geo, not so productive. So everyone uses Golang on their page to make sure you find what you need. So search for Golang and IDEs, you'll find a nice wiki page with all these listed out. Eclipse, IntelliJ, Emacs, and Vim, and many others have Go support. That includes invoking things like GoFunctor, Go imports, doing GoDoc lookups, and more advanced things like code completion, navigation, and of course things like syntax highlighting, that's all there. There's no one Go IDE, right? This isn't sort of a lock-in situation. The Go team is taking the approach of giving you tools that meet you where you are. We want you all to try it. And so we want you to be able to integrate the tools into whatever environment you're using. And there are Eclipse and IntelliJ plugins, and the companies are starting to get behind it. We're starting to see a lot of interest. Go is significant enough now that the developer tools people are engaging those. And so I think that's great. I think it should just keep getting better. So I hope I've at least teased you a bit into going out and learning a bit more. I'd like you to, the place to start is the online Go tour, tour.golang.org. It's going to build on that Go Playground, which is an online interactive, lets you write and run Go code online. And the tour is going to take you from Helloworld all the way through to a concurrent web crawler and everything in between. There's a lot of stuff I couldn't talk about in this talk. The Go tour is a really nice survey of everything. And then when you want to go deeper, you go to this wiki page, Golang.org Wiki Learn, and that's going to give you courses of study on things like concurrency and server programming. It'll take you a lot deeper. There's a lot of great talks online. There's a lot of great blog posts as well. And there's a great community. Under golang.org/project, you will find mailing lists and other developer resources. People really like helping each other with this. People are excited about the language, and I hope you will be too. Thank you.
Any questions?
Yes?
I have a question on the defer statement you were referring to. I think from what I understood, you said it's analogous to a finally statement in Java, right?
You would use it in a similar way to make sure something happens when your function returns. You were saying defer, yes?
Yeah.
Yeah.
Should it necessarily be the last line in the method?
It's not the last line of the method. Search keeps going after this, right? It's right there in the middle of the method. So defer, that's a statement, my fault for not indicating the method continues. So this is the search function. We hit defer, and then we continue on and parse that JSON result. And so whether we return here or here, that response body is going to get closed. Right? It's just pushing it onto a stack of functions to execute on whenever this function returns. Good question. Yes?
So
if a Go routine is a channel consumer, is there any way to add specific requirements other than just knowing the channel name? Is there any other permission you can do for?
You can, yeah, so you can restrict a channel data type to be send only or receive only. And so sometimes you'll use that if you want to create a function that only sends or receives. Let's see if I have an example of that. I don't think I have one here. Yeah, in my case, I just closed over the channel, so you didn't see that. But I could create, you know, I could say this function takes a channel C, which is a send, this is going to be send only channel of result. Right? And then I could pass C as a parameter here. Sorry, let's give it another name. So C2, right? Right. So now I've got a function that takes a parameter, which is a channel that it's only permitted to send on. Right. So this is one way to decouple things. But the funny thing is, you don't actually see channel parameters a lot in Go programs, and the reason is that more likely what you do is you provide a simpler interface, like we saw with first, where it's actually giving me a great excuse to make a point I meant to make earlier. Notice here when we invoke first, you don't know what first is doing. You don't know that it has channels and Go routines going on internally. It's just a blocking function call. And this gets to the point I was trying to make earlier about HTTP GET, and anything else just sits there and blocks, is that Go really embraces the imperative programming style that when you need concurrency, the caller introduces it, but at an API level, you don't need to expose it. You don't need to expose callbacks, you don't need to expose features. It's really just, you provide blocking functions, and then you use Go routines and channels mostly for wiring, mostly to structure your invocations of various things, and to do things like these timeouts and hedged requests. But it provides a really nice decoupling at the API level. You can keep your APIs very simple. But yeah, thanks for that. Yes?
How do you execute these examples? You have the piece of code on the screen and then button run. So what's behind?
Excellent. Yes. So the present tool. Let's see if we can pull this stuff up for you. In my terminal? Yes. I need to make this larger, don't I? And plus this. Let's go to Emacs. Yeah. All right. So you wanted to see Google first. Right. So this is the entire source code for that program. So you can see it has all the stuff we saw earlier. It has the result, the search declaration, the fake searches for Web 1, Web 2, that Google function, first fixes. So that's the whole thing. These are all stuff that we presented along the way. But for that particular slide, I just wanted to print from this start to this stop. So in my presentation, we're going into which presentation thing I use. I just say, play, go for Java programs, go first from start to stop. And so it just generates the slide. And then when I hit that run button, it's compiling and executing a program and capturing its output. It's all running locally on my machine. Yes?
Similar to Dart, like, how do you specify the number, if you have more number of cores in the machine, like, how do you specify?
Good, good. Gosh, I want a network connection now, because I want to show you like the online Go documentation. So if you go to go.org, or if you go, so the answer is there's a runtime package and it has a function called go max procs, and you set that to whatever number you want. And that informs the Go runtime how many processes to use. Let me see if I can get our network up. Wait, so now it thinks I have a network. Let's see. Go.org. Lies. Damn lies. I can't do that on the browser, can I? It could. Okay. Oh, see, yeah, this one remembers my login. There we go. So you were asking about the runtime package. So here's go.org, the index of all the open source web, all the open source Go packages. I search for runtime and find the standard runtime package at the top. So here you're seeing some Go generate documentation. Should look familiar when you're used to Java doc. You get an index of all the functions and data types. And here's that go max procs function. You give it an integer and it tells it tells the runtime how many threads it should be using. So within Google, we actually set that dynamically. We periodically ask the cluster management system how many cores are we allowed to use in our machine, and we adaptively set the number of threads in our Go programs, and that allows us to connect how much CPU usage we're using for Go programs with what the cluster management system wants to let us. So when it resizes a job, adds more resources, we can just take advantage of it. So this works out really nicely. Since I'm here, when you see a data type like func, it has a set of references underneath it. Here are the three methods for func: entry, file line, and name. We also see there's this func for PC. And the reason that one is indented here is because it returns a func. This is what I'm saying, there's no constructors, but there are static factory functions. Like you can just have a function that returns what you want. And GoDoc will say, okay, well you probably want to see that when you're looking at this data type. But you can have as many of these as you need, not unlike the named constructors in Dart, except for they're not constructors. I mentioned earlier that you don't actually need constructors so much in Go, and part of that is because you have those literals. So when you have essentially plain old data types, just records and such, you don't necessarily want to have to be bothered defining a constructor. Instead, you can just use a literal to assign fields to it directly. And so you don't need to declare a constructor here. I just declare the type, and then I can instantiate it with a literal. There's no getters, no setters, no nothing. I just create it. So this is just a value. Yes, sir.
So what machine architectures does Go support at this point?
Alan, you can help me with this.
We have machines. We have x86. We have 64-bit x86. We have ARM. We have what else am I thinking?
Sorry. So let me look at Go Arch, because I believe that gives me the
Yeah, I think it's just PowerPC. PowerPC was added.
Oh, actually, yeah. So here's the cross product, right? OS is an architecture, and I think there's a few more coming in Go 1.5. So we're currently at Go version 1.4. 1.5 should be out later this year.
And also the mobile devices are coming this year as well.
Yes. Yeah, actually, do I have a minute? The 1.5 release is kind of exciting. The reason it's exciting is because there's a major change to the garbage collector. To date, Go's garbage collector has been fairly simple. Obviously, Java has 20 years or more of garbage collector work behind it. It's very sophisticated. What we've done with Go in version 1.5 is optimized for low latency, because that's what we need with servers. So we're making the throughput latency trade-off, and we're saying what we really want is very low, hopefully close to zero, garbage collection pauses. The target is 10 milliseconds or less garbage collection pause time, and the results are looking very good. But what it does, it achieves this by spreading out the work, right, and running it concurrently, and in some cases as needed, barring off the mutator threads. But you're not. What it means is you're going to continue making progress. You're not going to have long stalls, but you essentially are going to pay a CPU cost to make to achieve that low latency. All right.
I have another question.
Of course.
So there's a trend right now with reactive programming, right? So
Does that mean like, oh crap, I need to fix this now? I don't know what it means.
that's DevOps.
Okay.
So the reactive style of programming. And then we have Go, where you said there's really, you want to avoid callback hell.
Yes.
So you have these two trends.
So is reactive callback hell? Or I guess I really don't know what reactive programming is.
Node.js,
Yeah,
so I did a lot of callback-based work in grad school using like asynchronous C++ for servers, because we were doing event-driven servers, single thread at the time, like high-performance web servers. But the issue is, and Alan, you and I have talked about this quite a bit, that when you have callbacks, you need to sort of pass all your bookkeeping along in the values you're propagating your callback. But that bookkeeping is exactly what would be on your stack in a straight line function, right? And so the thing with Go is you write a single thread and you have your stack, and the stack even grows dynamically as you need it. And so the bookkeeping just isn't there. Right? You have scope, you have stack, and it works. So the trends are moving independently. If people are embracing reactive programming, good luck to them. I've been there, and I like this better.
Any other questions?
And I have gophers. I'm not sure how to Yeah, right. So, yes, sir.
So people are moving away from pointers and It's like coming back to pointers, and why was...
So when you say moving away from pointers, you mean going to like algebraic data types or all, you know?
Because how, like the whole issue of dangling pointers and then garbage...
And no references and all that. Yeah, and pointers are simple and they're simple to understand. I think we did this has come up a lot in discussions. I think Go embraced, you know, we wanted the notion of values, of flat values, straight values to be there, and then you needed a way to then have a reference to a value and pass that around, so you can pass around a mutable state. Pointers were the natural fit. It's worth remembering that this is Ken Thompson in Runtime, reasoner. Go even has goto, don't tell anyone. But it's safe, don't worry. Yeah, I certainly pointers and even shared memory and databases, they're all, it's all there, and it's part of learning the language, learning how to do it as well. Other languages, modern languages, make different choices. There are some languages like Dart which say you avoid databases entirely with complete isolation between the isolates, right? They cannot share memory at all, which means you have to do everything through communication. So I can't pass a pointer to you, and we can't share mutable state at all. That makes a different trade-off when it comes to efficiency. That makes a different trade-off when it comes to how you break up your program and design it. Go's designed as a systems language, so there are, it makes a different set of trade-offs so that you can be efficient and have things that are allow you to leverage concurrency to structure your program well while not making your program really slow. I guess is the bottom line. But it's another way to think about it. Russ Cox suggested to me is that Go is a modern language and it embraces some new ideas, but they're the ideas that are very proven, that have a long track record of working well. So while Go brings new stuff, even the channels and Go routine stuff, while it looks new here, between CSP and now, there were a half dozen languages, especially at Bell Labs, but in other places, that explored those ideas and that worked out all the kinks. Right? So Go is building on those backs. And so part of the use of pointers and shared memory is like, you know what? We know that there are risks inherent with the way this is. The pointers are safe. You can't do pointer arithmetic. Okay, so actually I didn't get a chance to get into this. So you can't do pointer arithmetic. The type system won't let you. They are really more like references, but they're values, right? So you can pass them around, you can copy them, and so on. Yes?
So a few systems are written in Erlang and they're doing pretty well.
Yes.
Likewise, can you compare and contrast?
I can do it a little bit. I haven't used Erlang a bit, but I've read a bit about it. So Erlang is a much older language. It comes a lot from the telephony side. And it has a concurrency model called actors. And it is designed so the program can be transparently distributed across multiple machines. So each actor, which is actually much more like an isolate that you saw earlier with Dart, actors communicate through mailboxes, I believe, is semantics. So each actor has a mailbox where it receives incoming messages. The mailbox, I believe, is unbounded. It can, but messages can be delayed. I don't know if they can be lost, but what that means is that you program in terms of these actors. The programmer has no idea whether the actor is running locally or on some other machine. And I think Erlang also, similar to what you saw in Dart, supports dynamic code installation and upgrades in the same way that you replace an actor. Presumably you can propagate its mailbox along as well. So it's really trying to solve a somewhat different problem. I believe you could certainly build something like that with Go. You can easily use channels and Go routines and slices and so on to build a mailbox and provide that abstraction if it turned out to be right for what you wanted. I have a talk called Advanced Go Concurrency Patterns. It's a sequel to Rob's talk. And I go into a fairly sophisticated streaming example where I use something like an actor-like pattern. Essentially, if you have a Go routine that has a loop around a big select statement where it's handling different kinds of messages, it starts to look a little like an actor model. So another way to think about it is that channels are a fairly low-level concurrency abstraction that you can use to implement a lot of different patterns, and actors might do well.
Is Google discarding Java?
Is what?
Google discarding Java.
Is Google discarding Java? Hey, Kurt.
No.
Tech lead of the Java libraries team at Google. Yes, the answer is no. Go is being, I said Go exists to address certain challenges and problems that we saw as Google started to scale. But Java is alive and well at Google, and a lot of people love it.
Hi.
Yes?
Are there any talks about how you achieved lexical closures?
Talks about the lexical closures.
It's pretty traditional. I mean, it's a flat closure.
Oh, there's nothing specific in how you implemented it. I mean, Java is having such a hard time getting that to work.
I'm just going to do a
Probably.
Google search and see what I come up with.
So,
Yeah.
Understanding that as a concept is one thing, and then how you
Yeah.
achieved it is.
so essentially the compiler can see which variables an inner function refers to from the outer function, and they're allocated on another struct that's on the heap, and so that when the outer function returns, the thing is still there.
So there's this stack that you run, and also the lexical stack that you keep as a copy.
So they're always on the heap. Those variables that are referred to by the inner and the outer function are allocated on the heap, and so they outlive the outer function.
Right. So basically, the escape analysis determines that that variable is closed over, and therefore it needs to live for as long as either one lives. Right? So yeah, the nice thing about Go is you don't worry. I had this demo earlier where I said var n int return ampersand n, like return a pointer to the int that looks like, if you're coming from C, it just looks like I returned the pointer to something on the stack. But of course, it's safe. Yes, you return a pointer to an integer, and that integer lives as long as it needs to. So yeah, closures are the same way, right? You close over a value if it needs to live as long as closure will. Yes.
I think we're out of time. Thank you very much.
Thank you.